G'day there, Level 3 Physics. Brought you out here today with the Land Rover because we're going to talk about some banked corners, circular motion. Before we get into it though, I'm just going to do a few reminders on vectors from last year. Parking, right? We know that we're not moving. V equals 0. Well, what forces have we got acting? Downwards must be gravity, Fg. What's that one that goes up called? Equal and opposite to gravity? Normal force. Normal meaning at right angles to. That's critical. At right angles to the surface. So that's easy, right? Nothing more to learn. Except I know when I park on a hill, I've got to put the handbrake on or I'm bang in trouble. Forces, gravity, always acts down. We know that the normal force, normal, at right angles to the surface. Now we've got a problem, don't we? Because before we had the normal force exactly equal and opposite to gravity. Now it's not. Now we've got to add another third force into the equation in order to balance things. We've got to have, what's that force that's parallel to the surface? That's the friction force. And so speed 0, that means that those three vectors are going to add to 0. We can test that with a triangle, and we draw the gravity down, we draw the normal force up that way, and if all the forces are 0, that means our triangle must close. That means that that friction force must be that third edge. Note that there is a right angle in there. Cool? Let's move on. Okay, so let's just quickly burn through some revision of Year 12 concepts. When we're going around in circular motion, the velocity is always at right angles to the radius of the circle. We always call it the tangential velocity because the direction we're moving in at any moment is a tangent to the circle. And that direction of the speed is constantly changing. Direction of the velocity is constantly changing. The size of it, the speed, stays constant, we assume. Acceleration is centripetal, center-seeking, always directed towards the center of the circle. Look, we know from last year that centripetal acceleration is v squared over r, and we know that F equals ma, and if a is v squared over r, then F must be m v squared over r. Just putting those two equations together. And finally, the distance around a circle is the circumference, 2 pi r, and so the speed must be 2 pi r over t. The distance over the time, capital T, period. Time to go around that circle once. So let's have a look now at where Year 13 goes with this. So what we have in real life is we have a bit of a bank on the corners. Why do we do that? We do that to help the cars go around it. We use some of the normal force to help nudge the cars around the corner. That's good because if the corners are just flat, we're just relying on friction between tyres and road to direct us around the corner. That's fine in the supermarket car park when you're going slowly, but if you're on the open road and you hit a little bit of oil, a little bit of water, a little bit of ice, you want to have a safety factor in there so that the road is pushing you around the corner rather than relying on the tyres to get you around in case they lose grip. Now this is meant to be a banked corner, and that there is the back of a vehicle going around the banked corner. And so we're going to draw out what the vectors might look like on the back of that vehicle. I'm going to redraw it a little bit bigger for you in the middle here. Acting downwards, we always have gravity. We know that the normal force acts at right angles to the surface. Now that surface is banked, that means that normal force has been banked as well. Interesting thing though, in this kind of situation, we've got a piece of road under the car. That means that that car is not falling and it's not flying, and that means that the vertical component of the normal force has to be equal and opposite to gravity. They have to balance to stop the car flying away. So our normal force consists of those two components, the vertical one and the horizontal one. The vertical component is equal to the gravity force in size, opposite in direction, and the horizontal component, what does that do? The horizontal component provides the centripetal force. Some of it, all of it, sometimes even more than what's needed, but that horizontal component is going to be working towards the centripetal force. While we're on the topic, this is exactly the same sort of thing as what aeroplanes use to go around corners. You'll notice when you're in an aeroplane, if they want to change direction, the aeroplane leans to the side. And that's because the aeroplane runs on much the same sort of system as what the car does. Instead of having the road to hold it up though, it's got the lift force from the wings. So if that's your aeroplane in straight level flight, we got the gravity force equal and opposite to the lift force. If the pilot banks the plane, we've still got gravity acting downwards. Gravity always acts downwards. What's interesting though is now that lift force is no longer vertical, it's been directed off vertical. And so the vertical component of the lift force, that's what's holding the plane up in the air. Let's use a different colour. And the horizontal component, that's what's making it go around the corner. The complexity with an aeroplane, though, is that there's not a fixed piece of road holding it up. So if that pilot banks it off to the side, that lift force is going to stay the same unless the pilot alters something about the plane's flight, like the speed, the angle of the wings. Unless something's changed, that lift force stays the same. So as you start to tilt the plane to corner, there's less force up, same force down. Gravity is always the same, and so the plane might start to drop while it's banking, unless something has changed about how the lift force is generated. And so we just need to be aware that there's that extra complexity with the aeroplane situation. Let's do an example, work out what kind of bank we've got to put the road on in order to get a car around without relying on the tyres gripping the road at all. What about Horseshoe Bend on the Takaka Hill? Radius, I reckon it must be about 25 metres, something like that. Like the road must be at least 6 metres wide each side. In the middle must be something like 10 or 15 metres, something like that. Let's go with 25, that'll work. And say we want to be able to having cars going around there, I don't know, how fast do you think? 35, 40 k's? Maybe 50. Let's say we want them to go around at 50 k's, around about 15 metres per second. we're going to start by working out just how much centripetal force we need in order to get that car to go around that corner. Pause the video, see if you can work it out, otherwise I'll do it for you. We're going to need a mass, aren't we? Let's put in 1,000 kilograms. $9,000 newtons I make it. So how much of a bank do we need to have that corner on in order to provide 9,000 newtons? Let's draw a picture, that always helps. There's the surface of the road. That's the angle from horizontal. There's the car. We know it's got a mass of 1,000 kilograms. 9,810 newtons. And so how much must that angle be? Well, let's draw on some other things that we know. We know that the vertical component of the normal force has to be equal and opposite to gravity. So that's going to be 9810 as well. And we know that the horizontal component has got to provide all of that centripetal force, because we're assuming that it's an icy day and there's no grip on the road at all. 9,000 newtons. What sort of angle do we have to put that road on? Gosh, it's quite a bit, isn't it? Now, take a step back to your geometry class if you don't believe me, but that angle there must be theta as well. So theta has to be anti-tan of 9,000 over 9810. It's going to be quite close to 45 degrees. $42.5 I got. Give you some examples to work on.